really good and turn up right after.
Welcome and good evening. Or good afternoon. I'm Meredith Vaughn. I'm the Associate Director of the Center for Research in Mathematics and Science Education here at San Diego State, or CRMSE, as we like to refer to ourselves. And I'm also a science educator at the School of Teacher Education. And I'm really pleased to welcome you to our distinguished lecture this evening. CRMSE's Distinguished Lecture Series brings together mathematicians and science educators to come to our campus to engage with us as faculty and students and teachers and community members. And so we're excited to have you all here, and we're especially excited and thrilled to welcome Dr. Helen Quinn. Dr. Quinn is a professor emerita of physics at the Stanford Linear Accelerator Center and also a member of the National Academy of Sciences. And then in addition to her distinguished career as a physicist, Dr. Quinn has long been interested in issues of education. As a member of the National Academy, she chaired the Board on Science Education. She also chaired the National Research Council Study Committee, which developed the framework for K-12 science education, which many of you know lays the groundwork for the next generation science standards. And among many other things, currently she's working with Stanford's Understanding Language Project, where she chairs the science work group, and recently produced a white paper with Oki Lee and Guadalupe Valdez titled Language Demands and Opportunities in Relation to the Next Generation Science Standards, or VLLs. So this evening we are thrilled to hear from Dr. Quinn as she shares with us how science classes can contribute to language learning and how language learning can contribute to science classes. Please join me.
So, I'm going to talk about science and the new model for science learning that comes out of the framework of digital science education. For those of you who were at my talk yesterday, there will be some repetition and some of the slides you've seen before. I don't think it ever hurts to hear things twice, so that's okay. But for those of you who weren't at my talk before, you'll need that as context when I'm talking about when I talk about science learning. Secondly, I have a very specific viewpoint on language learning. So before I go into my slides, I want to talk a little bit, because I think there is more than one model out there for what it means to learn language. And I'm very much in the camp of Guadalupe Valdez at Stanford, who says learning language is about learning to do things with language, not about learning language structures or vocabulary. You need language structures and vocabulary in order to be able to effectively do things with language, like express your ideas, or argue from evidence, or describe to somebody else what you've observed. But each of those language tasks is for a purpose, and the purpose is more important than the language structure, as long as you can achieve your purpose in communicating what you wanted to communicate. That, and as a language, I'm a language learner myself because I'm still trying to learn Spanish, and for my own experience, it's much more important that I can express something than that I express it correctly the first time I try. So the idea of, okay, students must speak in full sentences, for example, actually interferes with the expression of ideas. And so English speakers don't speak in full sentences when they're expressing half-formed ideas either. So thinking about what it is we want our students to do with language, and then supporting the students whose language is weaker to be able to do those things and to contribute to a classroom discourse where student talk is an important part of student learning. That's the issue I'm talking about today. Not how do you get them to have correct grammar or to increase their vocabulary, although they will, as they practice, get closer and closer to speaking correct English and to using a richer vocabulary. Okay, so that's a preface. Now let's go into the kind of science teaching I'm talking about, which comes out of the framework. The idea is that science learning should have all three of these dimensions. One dimension is, what do scientists do? What are the science and engineers for that? What are the practices they engage in as they do their work? Why do students need to know that? partly because only by knowing that can they know the difference between knowledge that is science and knowledge that comes from other kinds of traditions and cultures and sources. Secondly, because by engaging in the practices, they're engaging in work that allows them to undergo the process of conceptual change to get from their naive conceptions of the world to a conception which more fully integrates the learning that they're achieving in their science classrooms. That integration of new ideas into your own conceptual framework, which is real learning, as opposed to artificial learning, when you layer it on top, and both concepts are living there, and the student, when asked to solve a problem, refers only to the knowledge that, and conceptions of the world that they had before the learning, because the learning is just a layer, like the frosting on a cake, that's smeared on, but not actually integrated into their way of looking at the world. So, then having defined these three things, and I'll tell you a little bit more about what they are, the standards that are the next generation science standards, we, the people who wrote the framework on which the standards are based, said it won't work unless the standards really have all three of those dimensions in the standards. So here's one example, right? For grade 3, plan and conduct an investigation. That's a practice, right? To provide evidence of the effects of balanced and unbalanced forces, stability and instability as a cross-cutting concept which applies across all disciplines, understanding the conditions of stability and instability in systems. And finally, on the motion of an object, the core idea of physics that forces make things move, change the way they move, understanding and beginning to understand that at a third grade level, which won't be full understanding of these laws, is a step towards the understanding of learning to build across the many years in school. So that three-dimensional notion that these pieces have to be integrated in instruction is very important. Which means students are engaging in these practices and using the cross-cutting concepts as tools to solve problems. That means there's a lot of talk in the classroom. Student-to-student talk, not just teacher-to-student talk, and student response to teaching. And so the classroom, being a discourse-rich environment, is a language-rich environment. And therefore, thinking about how to support language learners to both survive, to learn science, and to learn language in that environment is a valuable way of addressing how do we really use this time most effectively for students. Okay, so why three dimensions? Here's a quote, again I gave it yesterday, from Henri Poincaré, and it's there in French for those of you who read French, and it's there in my very rough English translation for those of you who read English only. But the point is that science is not just a collection of facts. That's no more than a pile of stones. So they say science is a construction based on facts, yes, but it's a construction of ideas, of theories, and of explanations. And that process of construction, like building a house, requires more than just the material to build the house with. So if you think of the dimensions, so students must build their own three-dimensional knowledge structures, and in order to do that building, get from their preconceptions to the science conceptions, of course they need the knowledge, they need the core ideas of the disciplines, they need some introduction to the ideas that scientists have developed over hundreds of years, but in the context of solving a problem where that knowledge is useful. And next they need the tools and practices and the experience using them. That's the science and engineering practices. You can't build a house if you don't have any tools. And thirdly, you can't build a house unless you know what a house is. You have to think, you can have all the wood in the world and all the tools, and you will not build a house unless you have some idea of where you're going as you try to put those pieces together. So the cross-cutting concepts are the metacognition pieces, the concepts that you need that provide tools for where do I go with these things? And that is why it all needs to come together in the learning so that the students really can do this constructive learning in their head. Here's the list of practices. All of them are discourse rich. The ones in red are ones that generally in inquiry-based classrooms have, I think, been underemphasized. So students for years have been saying, people have been saying, you know, you should be doing hands-on science and students should be investigating things. But it's no good investigating. You don't analyze what data you got. And you don't ask, how does that data correspond to the idea you had that was an explanation for what you thought would happen, or the model you had as to how that system functions. So the analysis parts, which are the discourse parts, are much more stressed in this view of science education. And therefore, language and language challenges become more important to think about in everything you're doing in the classroom. Not that they weren't important before, but if you're asking students to talk to students, then you have to support an atmosphere in the classroom where all students' voices are important. The inclusion that says, even though I expressed my idea without being able to say it right because I don't have enough language to say it right, that idea is part of the building of consensus and ideas in the group. How do I support the student whose language is weakest to contribute? He may have the best ideas about the science, but he may not be able to express them. So figuring out how to support a range of language ability along with a range of science ability, this is a challenging task for teachers. But it's equally important to think about the language aspect of it in order to teach the science, as it is to think about the science aspect of it in order to teach the science. So supporting the language learner actually turns out, since no kid arrives at school talking about science like a 12th grader even. So every kid is a language learner in the science classroom. And things that you do to support language development in the science classroom support all students, not just the ones who happen to be labeled as language learners. Of course, the ones who are labeled as language learners may need a little more support. But the idea that thinking about and supporting language development in the science classroom is an important part of teaching science is one of the ideas underlying my talk here. Okay, here's the list of cross-cutting concepts. I'm not going to spend a lot of time talking about all of these, but each one of these, think of it as a generator of questions. If I am thinking about a new problem, I'm trying to solve this problem, I say, okay, what's my model for this system that I'm looking at? What is the system? How do I model it? What are the mechanisms of cause and effect? What are the patterns that I'm seeing? How do I explain those? So each one of these concepts suggests questions I can ask in order to solve whatever problem I get to. And that's the reason why they're very important to stress. In science education generally, we sort of under-stress these things and stress the particular pieces of science knowledge we're trying to teach. But in fact, in order to take those pieces of science knowledge and apply them in the context of a new problem, these ideas and the questions they generate are very important tools for learning too. But questions are language too. So even being able to ask a question as to, you know, what did I notice here and what patterns are happening, that's a language task. And to communicate to others, well, I noticed this and I observed that and I think this pattern might be related to that. Those are all language tasks at the same time as their science learning tasks. So figuring out how to do this complex job of supporting both the language and the science is something that takes teachers' practice. There's several groups that are working on this. I point to the group from the Inquiry Institute at the Exploratorium, for example, in San Francisco, who've been working with kids in the Santa Rosa School District. And their work is showing that not only do these methods support science learning, but they really support language development and literacy development of the kids because they get so engaged in the science problems that they want to talk about them. And they're motivated to express their ideas because the science gets them interested. And then they're motivated to read and write. So one of the important practices in the science classroom, particularly at the elementary level, is having kids keep science notebooks. Science notebooks are very informal, so they can write in whatever language they choose to write in. They draw diagrams, they collect data, they keep a record of it. Now, when they're asked to do the formal piece of science writing, they have a basis for which to build that. And even if their notebook is in Spanish, their formal writing is going to be in English, that transition is supported because they've done the thinking. And they've developed their ideas and to some extent expressed them in English in the classroom. The interplay. And you'll find for a language learner child, the science notebook will actually be mixed in terms of what languages appear in. Because they're learning new science words and they only know those words in English. And yet they have other words that they only know in Spanish. So that's fine, or whatever language it is they speak it. I pick Spanish simply because that's the biggest sample in most schools in California. But figuring out how to support children to transition and to use whatever language resources they have to help develop their English language resources and their science thinking. And to respect the thinking as being the critical piece. It means accepting contributions no matter how they're expressed. And then helping move on. So the kid says something which is not really very clear because they haven't expressed it clearly. The teacher has options like saying, well, I think what I heard you say is such and such. Is that what you meant? That's accepting the contribution. It's giving an example of reframing that might suggest better ways to say it to the kid, but not saying, you didn't say it right, this is the way you should say it. It helps a lot to really, and then to allow the students among one another to use that tool. Well, I didn't quite understand you. Can you try again? Or I think I heard you say this. Modeling the things you want students to do in student-to-student discourse as part of the teacher-to-student interaction. Asking questions to prompt. A student has expressed a little bit of an idea, and you say, and does that mean? Or, and how can you tell us a little more about that? Or whatever it is you need to ask. So using questioning strategies that support not just the science learning, but also the language expression and the language inclusion of the student in the classroom. Very, very important. And this frame of three-dimensional science learning provides a lot of opportunities for that. So let's think about it. In the science classroom, how do you learn science? Well, you have to have opportunities to practice applying the ideas in the context of real problems. Right? The ideas in the abstract don't have much meaning for students, particularly for young students. They need to be learned in context of phenomena where, say, the idea of air pressure helps me explain what happens when I blow up a balloon and why the balloon goes and goes down again if I let it go. So taking real phenomena and using them as the context in which to introduce the science idea. That means you have rich and varied contexts appearing in the classroom, in phenomena and materials, and that creates an opportunity and a desire for the students to engage with realia, with real things. And that means, and to talk about them. But that means you need the words to talk about them. So the fact is, science has a lot of very science-specific language. Why? Because in order to talk about things, you need the specific words. And if I'm trying to explain how your bicycle works, and I say the thingamajig goes around and the what's it does this, it's not nearly as good as if I say the pedals go around and the chain connects the cogs and the gears to the cogs on the drive shaft that you're pedaling with. So the whole language that is developed for specifically saying what I specifically want to say is needed to talk about science. And therefore the student needs it and wants it and learns it, not because you gave them a vocabulary list, but because they need it to tell their idea to the next student there. Of course, to learn the science, you need all kinds of support from the teacher that helps you understand what it is you're supposed to be learning out of this lesson. And you need that the teacher accepts the student's expression of their science ideas incomplete and flawed in the sense of this is what the real scientists say. You don't say, when the student expresses an idea, oh no, that's not right, it's this. You say, well, that's an interesting idea. How would you test to see if that idea works? Or how would you refine your model to make it more like what we're actually observing here? The whole support of the student doing the thinking and the student building the knowledge requires you to accept their ideas even when they're wrong or incomplete as the basis for the further learning. And not to be always looking for what's the right answer here. So that's learning science. Now look at learning language. Story's exactly the same, folks. You need a rich context with opportunities to use and repeat and use the language in context. You need the equipment, the things that make you, that you want to talk about and that make you want to speak. One of the biggest barriers for language learners in the classroom is opening their mouth and saying something, because they know they won't say it right. And if the classroom is a classroom where right and wrong is all that matters, then I better not keep open my mouth. But if the classroom is a classroom where ideas are being pursued and you're dealing with stuff and you're trying to explain something that's happening, the kid with limited English has just as much opportunity to get engaged with the phenomenon as the kid with very sophisticated and complex English. And once they're engaged with the phenomenon, they're very motivated to say, express their ideas and respond to other students' ideas. So one of the things that the science context gives you is the motivation to speak, the motivation to write, the motivation to listen carefully to what somebody else is saying and understand it. Because that's what you have to do to engage with the phenomenon. Of course, again, you need appropriate supports for the learning. And you need, as I've said several times already, you need acceptance of incorrect language and incomplete sentences and struggling to express yourself. And that's true as much for the English learner as it is for the student whose English is competent, but because they're still struggling to understand this particular phenomenon, they haven't really got it formed into a very well expressed idea. That's fine. That supports language learning. Move ahead to the other slide, did I? How language develops is the other slide. It says the same thing. So the whole piece of how does it work, there's a very strong parallel between science learning and language learning in a phenomenon-rich science learning experience. And so it makes, therefore, it's natural that the science provides the context in which the language learning occurs. And the language learning is necessary to support the science learning. So a science teacher tends to reject, my job's not to teach language, my job's to teach science. But you cannot teach science unless the students can express their ideas, and the students can read what they're expected to read, or they can write what they're thinking in their science notebook. So if you structure your science classroom around science understanding, you're structuring your science classroom around language learning too. And therefore, it's a natural pairing to make this. Of course, it's not a language learning opportunity unless you really pay attention, manage to assure that the culture of the classroom respects ideas rather than individuals' power in a hierarchical power structure in the room, respects contributions, and provides a variety of supports depending on the level needed for the different students in the classroom. A juggling act, I agree, for teachers, but this managing for inclusion, if you're going to have a discourse-rich classroom, managing the culture of that discourse is an important part of making that classroom work. Just as managing the seating of the students and the grouping that they're moving into, and how all of this is part of classroom management that plays into who's learning what when, and figuring out how to structure your classroom and to develop that culture where it's okay to disagree with somebody, but you don't say you're stupid. You say, I don't think I think the same way. I have a different idea. Here's my idea. Let's compare and see which one works best. The whole culture of argumentative discourse is something students generally have not learned outside of the classroom, because our culture today is not very good at argumentative discourse, with the argument being based on evidence and not on who's more powerful or who's louder. So building that culture so you can have real argumentative discourse between students in the classroom, that's a piece of support that is really important, and part of that is making sure that all voices get heard, no matter what the status of the student is in socioeconomic terms or in language development terms. So these messages are obvious, but it's not easy to do. Making it happen that way takes really thinking through how do you structure and have the students really integrate a set of rules for behavior into how classroom discourse happens. And that is common across whether it's classroom discourse in math, or in science, or in language arts, or any place else in the classroom. So trying to develop in the school a culture of argumentative discourse in the classroom, important too. Now let's look at some really science-specific issues in language, right? Yes, there's a lot of technical terminology. That is a challenge for all students, because students don't come in knowing the science vocabulary. So there's the language learning around technical language. There's the words like analyze, consequently, they're called academic or level 2 or whatever language words. Again, very students enter into first grade speaking that way. So all of them are going to be learning this language in the classroom. And supporting the building of that language and the usage of that language. Again, the exploratorian people, I was talking to the second grade classroom and the third grade classroom. They've been doing it for a couple of years. The students enter the third grade teacher said, it's really amazing. The kids are coming in and they say, my claim, I observed this and my claim is that. Well, that's language they've learned by doing it, by practicing it in the second grade classroom. And now they bring it to the third grade classroom, and it makes it easier for the third grade teacher to build on that and take it a step further. And say, therefore this happens, or consequently that happens. Be able to add those links. You're not going to read those words necessarily in second or third grade, but you can use them. And thinking that students' language usage and their writing ability or reading ability is totally linked is another place where we have to break down some things. Young children can use very sophisticated language if they learn it in context and in practice of use. And then when they have to read it, they have it to be able to use. So supporting that. The other thing is, if you're trying to read science, we as scientists tend to write long, multi-clause sentences. Why? Because we want to put in a lot of qualifiers and conditions and be very specific about which. And you know what hangs up the kid? It's the word, the thing, the whatever, that, did that. The that or the which or the connectors. If you take the that and think it refers to the wrong piece of the previous two clauses in the sentence, you're not going to understand the sentence. And so it's actually not always the technical words. It's the structure of the sentence which is throwing the kids. So helping students really read, and all the strategies you learn in English language arts classes don't work for reading those sentences. because you cannot speed read or get the general sense of the sentence and make any sense out of it. So in fact, when I read physics, I read a lot slower than when I'm reading a novel, and I read differently. And I need somebody to teach. I needed to learn to do that. Or I take my strategies and apply them to the science textbook. They simply don't work. Thirdly, the whole idea of words that express a complex idea. Take deforestation. There's a whole story in there, right? Somebody cut down the trees, and it led to the fact that this land doesn't any longer have trees on it. Well, that's not just one word, that's a whole story, right? So, and science tends to do that. We invent these words that tell whole stories. And recognizing the structure of words where nouns can have whole stories involved in them is worth talking about in the classroom. Inspiration, adaptation, it goes on the list. And then the story of precision. However, I've said this already, so I won't repeat it. Let's look at science-specific language learning opportunities, because there's a balance. Yes, there's challenges, but also one of the things is when you look at a science textbook, it's not just words. It has diagrams. It has graphs. It has tables of data. It has maybe equations, right? And dealing with all of these things actually helps interpret the language. But again, in the language arts class, a student has never learned that there's 5 sources of information, and now I have to coordinate them all to come up with a common understanding of what this book is telling me. So how do I look at the picture and the caption under the picture, and I look at the graph and the caption under the graph, and I look at the text, it's in paragraphs, and I put it all together to come up with a single understanding of what this book is telling me. That's not something you're going to learn any place outside of the science class. And it has to be supported for all students, and particularly, but it provides a path in to reading the text for the language learner, because they've got other sources of related and similar understandings that are not just verbal. And therefore they express, they help make that connection to the verbal text. The other thing, which for language learners is, science is rich in different topics to explore. Whether I'm doing physics or I'm doing biology, even in the context of a physics course, I'm going to bring up many different phenomena, and therefore many different areas where there's vocabulary to be learned. And so the diversity of topics being explored broadens the language learning opportunity, and you don't have to artificially introduce some vocabulary because you want to learn. We introduce it in the context of what's needed to talk about this problem. And then doing design opportunities, design work, which would put engineering in with science for multiple reasons. One of them being that for students coming from families where science has not been part of their background and culture, the fact that science is useful in the real world and that we use it to support designing new things is an important reason to want to learn science. So the design opportunities also bring with them language opportunities, because students who are designing things really want to tell other people what their design is and why they think it will work the way it works. So again, the design work gives motivation for language development. So, as I've said, I'm going to refer you to a document which helps see this. Let me go. So here's one of the science practices. This actually comes from the paper that was mentioned that I developed with Guadalupe Valdez and Roki Lee, saying when students are doing a science task, such as developing a model to explain a particular system, what do they have to do? Well, they have to do some thinking tasks, which is what's called analytic tasks up here. They have to develop and represent an explicit model for a particular system in order to explain a particular phenomenon. But as they do it, they have to do language tasks. They have to listen and read, and they have to speak and write. In order to describe their model to other students, to compare their model with the model another group of students has developed, to discuss strengths and weaknesses of models. So there's a lot of language tasks associated with doing the science task. This table comes from our paper, but then the document which I referred to on the website of the Council of Chief State School Officers, they have a table like this for every one of the science practices, for every one of the math practices in Math Common Core, and for every one of the language arts practices. And the language arts standards call them something, and the practices they call them student qualities or something like that. I forget exactly the terminology, but the point is these tables help the teacher know, are their students doing this practice? But they also help the teacher think about what are the language tasks I'm asking the student to do, right? If a student has to be able to take another student's description and understand it in order to respond to it, that's a language task, right? As well as a science task, so it's a learning task. So thinking about these science and math practices in terms of the specific language demands of doing each practice, I think is very useful, and that set of tables provides a starting point for a discussion with teachers about what their students are doing or not doing in the classroom, and how language support is needed to help particularly language learners undertake tasks like this. So that's useful. Here's an example of modeling, right? You know, there's not a lot of work. This is an assessment task, actually. So it asks the students to label. You can't quite read it, but the idea is the student is given the picture of a gas and a little lens, and this is what the magnifying glass, if you had such a good magnifying glass, sees, to look at what's going on in the gas. And the students are modeling here. But they have to write some specific words to describe the symbols in their model. Just writing the key to the model, that's a language task. Right? So the whole game of building up how you describe what it is you're trying to communicate with this diagram shows that even when you're doing diagrammatic work, it's developing language as well as developing science understanding. We have ammonia molecules, that's language. Right? So, the challenge for the teacher is to take what they know about science and science learning and to integrate it into it and learn to think about, well, what are the language demands of what I'm asking my students to do as they're learning science, and how can I support students at varying levels of language to do those tasks, just as I think about how do I support students at varying levels of science understanding to do those tasks. It's a big demand on the teacher, and it doesn't work to just say, here's what you do for language, and here's what you do for science. You really have to say, here's what you do to support language development in the science classroom for it to work. And then teachers can get it and really run with it, because it's not about language for the sake of language. It's about language for the sake of learning science. That's the way the science teacher sees it. But for the student, who cares? If I'm learning something, I'm learning something, right? So this is the message I'm trying to convey. This is about, well, how do you do it? First, you set up a good science situation. Right? Something which will stimulate the discourse, something that the students want to explain. And then you support the discourse and think about it, and flexibly and differentially arrange student groupings in different parts of the task. And you prompt and question to elicit student thinking, but also at the same time you're eliciting student speaking. And so the whole process is very, very rich in terms of the opportunity it provides. And where it has been done with attention to using science for teaching language, it is demonstrated that this works. That this really is a powerful way, not only of supporting science language, but of supporting language learning. And mathematics too, if you integrate that in at the same time. So depends on the task, depends on when you ask for it. But the idea that, particularly at the elementary school, where one teacher is teaching everything, it's not about language time and science time and math time all separate all the time. Yes, sometimes they have to be separate and the focus has to be, this is a math exercise, this is a problem designed to elicit certain math learning. And over here, this is a science problem that's designed to elicit certain science learning, but both those problems can also elicit language learning and reading ability development and literacy development. So figuring out how you do all of this together is, and it's different like at the elementary school where one teacher is trying to teach them all, and at the high school level where the focus of the teacher is generally much more disciplinary based, but they have this range of language learner levels in their classroom and need to figure out how to support all of them to learn science. Okay, so I think my time is up, and I just leave you with a few more statements about what science teachers can do to support language learning. It's rich, it's varied, and it just takes paying a little attention to that piece of what's going on in your classroom, as well as to the science learning you're trying to elicit as you design the activities and groupings and culture in your classroom to make the science learning work. You can think about what also it can do in terms of language and literacy learning. I will stop there and let you ask your questions. Yes.
So you had mentioned that science notebooks can be written in students' home languages, which allows the students to think through before they do their formal writing. What do you suggest for pre-literate who come in without writing skills?
Diagrams. Right. Starting with express your idea whatever way you can. And then, okay, what words do you need? Tell me what's in this picture. And maybe we need to provide you with a few of those words and show you how to write them. But, and of course, it's really hard at the high school level if you have kids coming in without the literacy, even in their home language, then that challenge is much larger because they really, those kids have developed an education deficit that takes a lot of work for the teacher to overcome. So I'm more thinking about the kids who, when they arrive, have some level of literacy and some level of math and science even in their home schooling and their schooling before they came to your school. But yes, for the kids who arrived at high school pre-literate, that's a real challenge. Different challenge than the pure language learning challenge. Because they have so many other learning challenges as well.
I had a follow-up question to that, but before I do that, as an English language arts teacher and an ESL teacher, I want to say that actually English language arts classes are moving much more towards using those different text features, the graphs, and all of those things.
They are today.
Yeah, and the
Right.
Common Core has been pushing that, but some places have been doing it for 5 or 10 or even 15 years.
Mm-hmm.
So if you feel like you need help with teaching kids those things, go see the English teachers at your schools.
Yes.
Because they're getting a huge
And
dose of this in Common Core right now.
the communication across teachers, across disciplines, which is generally rather weak in schools, is very important for doing this cross-discipline. So at the elementary school, it may be one teacher, but the high school is 3 teachers, or 4 teachers, or 5 teachers dealing with the same student. If they don't know what one another's doing, they can't build on what one another's doing. So yeah, communicating, the science teachers have, in the last couple of years, been asked to do more on the language and literacy front than in the past. Not that they shouldn't have been doing it in the past, but it's a more explicit demand today. And science teachers will often resist that because they say, that's the language arts teacher's job, that's not my job. All I'm saying is, they actually have to both work together so that that skill is developed both places with consistent language about what it is you want them to do. So the science teacher may not know the language that the language arts teacher is using around these skills, and yet they're trying to teach the same skills. Well, it helps the students a lot if they're also using the same language to talk about those skills. For example, arguing with evidence, right? Evidence, arguments, whether it's in science or in math or in social science or in language arts, has plain reasoning and evidence. What's different in the different disciplines is what counts as evidence and what kind of reasoning they're expected to do. But if you use the same language about plain reasoning and evidence, the students can see the connections as well as begin to hone in on the disciplinary differences. And they need to be supported for both things, the connections and the differences. Yes.
It seems like through science, there would be a good support for academic language, right?
Well, specific types of academic language which scientists happen to use. Lots of other academic language which scientists don't use as much and other people would use more. So, yes.
I was just wondering if you have any suggestion as far as when you're teaching, trying to use the science background to teach language, if there could be a way of promoting also conversational language by means of the teacher being more accommodating.
Yeah, discourse in the classroom promotes conversational language as well as the language of the text that the students are calling. But you know, conversational language can also use academic words. They're not just for academic purposes. So really what's happening is you learn language by using context. And the context can be a conversation about science or it can be a casual conversation among friends. Right? And the language you need for those things is somewhat different. You can't do everything in one situation. What I'm saying is the science situation supports a wide range of language skills and language development. Yes, if I need words for my parents-in-law, I may not learn those words in the science classroom, right? But that doesn't matter because as you become more confident as a speaker of a new language, you very quickly adapt to using that language in new situations and learning the words you need for that situation from the context where you're having that conversation. And I think that the getting over the barrier of being a speaker and a writer in a new language is a big, big step into any region where you're going to use that language. So that using the science classroom to help get over that barrier is what I'm advocating here. I don't claim that the science classroom can do the whole job, but I think it can be very supportive of developing a set of skills which then carry people further outside of the science classroom.
Helen, thanks for a great talk, very interesting. My question is about undergraduate or university introductory science courses, physics, biology, chemistry. And I was wondering if you could say a little about where you think your talk made the greatest points of connection to those university courses and where there's the greatest disconnect between those types of courses.
It depends what kind of course. If I'm talking about a studio course at the undergraduate level, it's not so different from talking about a high school class with the students working in small groups. If I'm talking about a lecture to 300 students, I'm talking about something different. And there, the supports needed are different to be inclusive in the classroom. And I haven't thought that much about how this translates to the college level. So I'm not sure that I have very much useful to tell you about that. Back.
Could you talk a little bit more about how to establish trust and respect in the classroom? You talked about it a little bit in terms of letting them do.
You should ask somebody who's worked with kids in the classroom a lot more than I have. When you ask me, I can give you guesses, but this is not my area of expertise. I think it's really, really important. But classroom culture and classroom management, clearly is an underline, an underpinning for whatever you're trying to do with students in the classroom. And developing a classroom with what Sarah Michaels calls constructive talk happens around some subject area discussion that the students are having one to another. That isn't something that happens accidentally. It happens with really thoughtful teacher structuring of how to make it happen. And over time, a development of cultures of kids who in second grade have had a classroom culture of discourse can move to third grade discourse that's richer than the kids who arrive at third grade without having had that experience, and you, as a third grade teacher, trying to develop that culture in the classroom.
Yeah, you can see how.
And if they get all the way to high school before they have that, they actually resist. They say, why do you want us to talk about it? Just tell me.
Right.
Right? So, figuring out how to support that, because we know, in fact, it supports a different kind of learning. And yeah,
And getting students to speak up in the first place, if you're.
that's right. There's always the
learner,
student
you're
who's
not
going to
even
run
gonna
off
say
at the mouth. And there's always the student who will say nothing unless specifically invited to say something. And trying to figure out how to manage that so that all of the student voices come into play. It's not easy, and I don't claim to have all the answers to it. And I have not taught at the elementary level. I have taught at the college level, and it's a very different place for things like classroom culture. There's another question here in front.
Yeah, you mentioned the distinctness of specific reading strategies for technical material. You have science, but I'm more interested in math, but they're actually quite similar.
The issues are similar, at least, yes.
Yeah, and you say help students develop. So how do you do that? I mean, you assign stuff, typically they try and fail miserably and you get nothing. So you got something.
Right, so differentiate, for example, just taking one sentence and spending some time in the classroom discussing this sentence or this paragraph in the book, not as how it describes math, but as how language is used to describe math, or how language is, right? Having them really work at interpreting one thing, say once a week, would then really strengthen their ability to read the next sentence with you not there helping them interpret it. And so thinking about what do I need to do, not to say, oh, they can't read it, so I'll just avoid the textbook and tell them. To say how, because after all, they'll be able to learn math without you if they can read a math textbook, right? So how do you really use the textbook as a tool for learning to use the textbook? That's a trick, and it takes, and there are various people who suggested various strategies for it, but the specific thing is you have to assign something that requires the reading and support in the classroom work where the students are not just reading alone, but discussing reading among themselves, discussing a sentence and interpreting it, discussing a passage in the book, and saying, well, I think it says this, and the other one saying, well, I think it says that. Let's try and figure out what it really means, and how do I translate these words into mathematical expressions, or these mathematical expressions into words. That's an exercise that you go back and forth with several times before you feel comfortable doing it. So there's many strategies. I only know a few of them, but people who really talk about learning math through reading, or learning science through reading, or learning science to support being able to read science at the next step. Just recognizing that that's a critical learning too, rather than thinking, oh, their reading ability interferes with their math learning, so I'll avoid reading so I can work on math learning. It's really not supporting them in being able to go further. So thinking about how do I use the math text that they have, and some are better than others in terms of their ability, to focus on a small piece and talk about it from the perspective of how do I interpret what's written on the page to help me understand a mathematical idea.
We only have time for one more question.
Okay, I'll take one in front here.
You mentioned that the tables that were breaking down the demands of language, the analytical tasks, the receptive and productive language, were available on a website of the
Council of Chief State School Officers, CCSSO, and then on that website you look for resources, and under resources you look for a framework for English language development standards. So it was a document about how do you think about language standards for English language development that connect to the tasks that Common Core and Next Generation Science Standards are going to be asking students to do. And that's where that set of tables exist.
Please join me in thanking Dr. Quinn.